Alright, so today we're going to be going over the Lewis structures, and to start off with, we're going to need some definitions. Alright, so first of all, we're going to count the valence electrons. And remember, the valence electrons are just those electrons, in this row here. We're not counting any of the core electrons. One little thing here is when we are going through this transition metal region, we basically just ignore those. So really, it's just going to be the number of s electrons and the number of p electrons that we're actually counting. So really, all the valence electrons in this column are going to be 8. This is all going to be 7, 6, 5, 4, 3, 2, and 1. Okay. And also with the charges, of course, remember the electron is negatively charged, so if we have an anion that's negatively charged, we're going to add electrons to there. If we have a cation, we're going to be subtracting the electrons because, of course, that's positively charged. Really, most of the time, all of our ions we're going to be dealing with are going to be anions because there's only, ammonium and hydronium cations that we have, but otherwise everything else is going to be anions. So we're just going to be adding that charge onto there. So our first atom is usually going to be the central atom. So when we start looking at formulas like methane, CH4, we have the carbon's going to be in the middle, or sulfur dioxide, SO2, the sulfur is going to be in the middle, or chlorine dioxide, ClO2, the chlorine is going to be in the middle. There's of course some exceptions. Water is H2O, but here if we have the H in the beginning, the H is always going to go on the outside, and the reason for that is hydrogen can only take one bond, at least for anything that we're dealing with here. So because H can only take one bond, you can't really put it in the middle and bond it with multiple things. So the H is always going to be on the outside in those cases. Alright, then you're going to go there and place your remaining atoms around that central atom, and then add single bonds to there. And each bond is going to represent an electron pair, 2 electrons. So just remember, when you're counting your number of electrons that you're putting in your molecule, each bond is going to be 2 electrons. Alright, then you're going to go there and place the remaining electrons. Of course, these are all these valence electrons that we just counted, on the outside atoms to fill their octets. Alright. And less, of course, the hydrogen, which can only take a total of 2 electrons for that. All right, so of course, if you already have your one bond there, that's going to be 2 electrons, so the most you can really put around any atom is going to be 6. So if you have any electrons that remain after you've filled up the outside atoms, those go on the central atom, and those will form expanded octets. And we'll be looking at those in more detail. Usually the expanded octets are going to be, with these kind of ions down here. We'll see these things occasionally. Alright, now we're going to check the formal charges, which should be near 0. And there's a couple of ways you can actually calculate this. I'm just going to give you the simplest way. There's some other ways out there that are essentially identical, but they throw in extra factors of a half here that can get a little bit messy. So this is the definition of the formal charge, and it's actually quite easy once you get the hang of it, and we'll see this a bunch of times today. So formal charge, of course. Okay, so there's our little definition. The formal charge, and remember, the formal charge is actually going to be calculated for each atom in the molecule or ion. Okay, so you can't just calculate the formal charge for the entire molecule. You have to calculate the formal charge for each individual atom in the molecule. Now, usually because of symmetry, you'll just notice that a lot of them are the same. So you just have to multiply them out. So the formal charge is essentially looking at how the electrons arrange themselves, and this way we can actually find out if we're going to be needing double or triple bonds in our molecules. All right. So first of all, we're just going to be calculating the number of valence electrons in the neutral atom, and those are always going to be the same, right? Nitrogen is always going to be 5, oxygen is always going to be 6, the fluorines are always going to be 7, carbon's always going to be 4. So they're always going to be the same no matter what. Okay, so that's the nice thing here. And then you're going to have minus the number of lines plus the number of dots. Okay, now of course the lines are you're dealing with a single, a double, a triple bond, so that's just the number of lines we're going to see. And then the number of dots is going to be the number of unpaired electrons on the outside of the atom. Okay, and we'll be seeing examples of this in a little bit. There are some other definitions out there, and instead of saying the number of lines, they say 1/2 times the number of shared electrons. That's exactly the same thing as saying the number of lines, because essentially what you're doing is for every line you're counting 2 electrons, and then you're just multiplying it by half. So essentially you're just counting the number of lines. So this is a lot easier rather than taking it, multiplying by 2, dividing by 2, and it's just extra confusing. So right here, if you just know this, that will be very good. So what you're going to do is look at these formal charges here, and then if you have extremely large positive or negative formal charges on the atoms, well, then you can move the electron pairs around to make double or triple bonds. And that's going to reduce your formal charges, increase the formal charges on the other atoms. And again, we will see examples of this. All right, now if there are several possible structures with this, the more electronegative atom is going to have the negative formal charge. Essentially, these formal charges aren't, real charges in a real sense, but they do give an idea where the electrons are going to be hanging out more often. So if you have several possible structures, the electrons want to hang out with the more electronegative atoms, so that's going to be the more favored structure. Unless, of course, this is going to violate the octet rule. And again, we'll be seeing what we mean by, what can be violated, what can't be violated in a little bit. Here, the atoms up to neon cannot have more than the 8 electrons. Okay, so over here, here's up to my neon. These, and this is especially true right here, the carbon, nitrogen, oxygen, fluorine, these are the ones where usually we're going to see this, is that these cannot have expanded octets, meaning that these cannot take more than 8 electrons. The reason that these elements, from here on down, can actually have expanded octets is, as we're going to be seeing later, what's actually going on with these is hybridization. So we're actually mixing, s and p orbitals and as well d orbitals. Well, up to here, there's only available s and p orbitals to do the mixing. So that means you can only take a total of 8 electrons. When you get down here, there's the s and p, but then we can also start borrowing some from the 3d orbitals over here. And because we can borrow from some of these neighboring d orbitals, these elements here can actually have expanded octets, and everything else down here can have expanded octets because we can borrow from some open spaces in the d orbitals. But up to here, there is no such thing as a 2d orbital to borrow from, so therefore you cannot have more than 8 electrons for these. So that's where we just have to be very careful with those. So these are the nice rules here. One thing just to be aware of when we're talking about these Lewis structures is that they need to be taken with a grain of salt. These are back of the envelope calculations which give good approximations, but they are not, how everything is totally working, okay? So don't, be under the illusion that, this is, the way that the molecule is definitely arranged. These are just first approximations that you can basically do on the back of an envelope that work out very nicely in a few minutes without going through detailed quantum mechanical calculations. So just be aware there are limitations to these, and we will be seeing these limitations as we go on here. All right, so those are all the definitions, and now we're just going to work out some examples here so we make a little bit more sense as we go through this here. All right, so let's start with something really simple: water. All right, so water, of course, is H2O, and remember, from the first thing here, we want to count our number of valence electrons. So for water, we have 1 hydrogen, another hydrogen, so that's going to be 2 for those, plus another 6 for the oxygen. That's going to give us 8. All right, so just remember again, number of valence electrons is not going to be, 8 over here, the total number of electrons. All we have is, of course, the 1, 2, 3, 4, 5, 6. Okay, so oxygen, sulfur, selenium, tellurium, all these things here are just going to have 8 electrons. All right, then our next rule, the first atom is usually the central atom. Well, here, of course, we have our hydrogen. That's our little exception, so the oxygen is going to be our central atom. And then we're going to place the other atoms around the central atom and add my single bonds. All right, and then what we're going to do is place the remaining electrons on the outside atom to fill the octet, unless we're hydrogen, which we can only take the 2 electrons. All right, so right here I have 1, 2, 3, 4. And I can't put any more on these hydrogens because they're already taken up. And then this is just going to be 5, 6, 7, 8. All right, so that's going to be my total of 8 valence electrons. The next part, well, the remaining electrons go on the central atom. Okay, so that happened right there. This, is not going to be expanded octets always. Sometimes there will be expanded octets. We'll see examples with that later. Next, we're just going to check the formal charges, and these should be near 0. So again, this has to be for every atom in here. So this is the formal charge of the oxygen. So remember, there were 6 valence electrons. Okay, so just remember our definition: valence electrons minus lines and dots. That's going to be 6 minus my lines, which is going to be 2, plus my dots, which is 4. That's equal to 0. And the formal charge in my hydrogen, well, there's 1 valence electron for all hydrogens, and then minus 1 line, and there are no dots there. And that adds up to 0. All right, so these are both near 0, and great, we're done. This is the Lewis structure for water. One other little thing I just want to mention, which is a good double check when you're doing these Lewis structures, is that the formal charges on every one of the atoms inside your molecule should add up to the entire charge of your molecular ion. So right here, if we ended up with like a +1 or a -1 charge, Well, water is not charged, so then we would know we goofed up somewhere in our formal charge calculations. So right here, this is just a good double check just to make sure that you did all your formal charge calculations correctly. And at this point, we're done. We don't need any double or triple bonds in here because all our formal charges are zero. We have single bonds everywhere in here, and we are not violating any octet rules, so we're all good. Okay, water, easy peasy. Let's look at one a little bit more complicated, carbon dioxide. So here, valence electrons. So there's going to be 4 for the carbon and 6 for each of the oxygens. That's going to be 16 valence electrons in there. My first atom is my central atom, and then I'm going to put the oxygens on the outside, and then add a single bond. And at this point, I'm going to add the rest of the electrons. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Now we're going to say, all right, well, what are my formal charges for that? So this is going to be, again, 6, and my number of lines is 1, plus there are 6 dots around there, right? So that's going to be a -1 formal charge. And also just note, I have 2 oxygens which are exactly the same in here, so really this entire thing I'm just going to multiply that by 2, because I don't need to do this again because it's going to be exactly the same here. Then I have the formal charge on my carbon. That's going to be 4 minus 2 lines and no dots. And that's going to be a +2. Of course, I add this up, +2 minus 1 minus 1. It's going to work out to be 0, so I did my formal charge calculations correctly. However, if you look at this, and obviously here the charges are not near 0, so that means I need to start moving electrons around to make these things closer to 0. So notice right here, if I have a negative charge of 1, that means the oxygens over here have an extra electron pair that they really don't need. My carbon has a +2. He really wants electron pairs. So what we're going to do is basically take one of these electron pairs, move them over here. We're going to take one of these electron pairs over here, move that one over there. So every time I do this, my formal charge of my carbon is going to drop, and my formal charge of my oxygens is going to rise, because now I'm sharing, so this is getting less negative, and since the carbon's gaining electrons, it's becoming more negative over here. So I'm just moving these over and making these into bonds, okay? So my new structure here is going to be the carbon with a double bond on either side. And now just to show that the electrons did move the way we thought they did, well, this is going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay, so still I got my 16 valence electrons. And notice right here now, this only has 4 dots around here, because this is going to be 1, 2, 3, 4, 5, 6, 7, 8. So this oxygen has that complete octet of electrons. The carbon has a nice octet of electrons, because that's 1, 2, 3, 4, 5, 6, 7, 8. That has it around there, and this oxygen is exactly the same. So really this is, kind of what we would maybe expect as well anyway. Then we can just go through here, calculate my formal charges, and we'll just do this for the oxygens again. So it's still going to be 6. Notice in all these, the ones I did from here, the water, this one over here, that one over there, the oxygens are always going to be 6 for the number of valence electrons, because that's universal, what I'm starting with for the neutral atom. Okay, so that's always going to be the same. And then subtracting off here, I have 2 lines and 4 dots. And that's going to be 0. And the formal charge on my carbon is going to be 4 minus my 4 lines, right? Plus no dots, which is 0. Add that up. That's going to be 0. And of course I would technically multiply that by 2, but that doesn't really matter. All right, so at this point, that's going to be my structure here for my carbon dioxide. All right, next up, let's try carbon monoxide. Now this one is deceptively simple, however there are little tricks to this that we just have to be aware of. So here my valence electrons is going to be 4 plus 6, which is equal to 10. And we just start off here. There's my carbon with an oxygen next to it. Okay, we don't have to really worry about central atoms when we just got 2 atoms in here. And then that's going to be 1, 2, then 3, 4, 5, 6, 7, 8, 9, 10. So at this point, I have to go through and just calculate my formal charges. So this is going to be for my carbon. It's going to be 4 minus, what do I got here? 1 line and 6 dots. So that's going to be 4 minus 7, which is going to be a -3. And the formal charge on my oxygen is going to be 6 minus 1 line and 2 dots, which is going to be a +3. Of course, you add that up, and that's 0. Now, obviously, right here, we have this problem. We have, positive and negative 3s. Those are way away from 0. So what we need to do is move my electrons around here. And really, I would move one of these over here, because remember, this is the -1, and it wants to go to the +1. So I'm going to move one of these electrons over here. And at this point, I would have a triple bond. And I can't move any more over because I can't have quadruple bonds in these things here. So triple bond is as much as I could go through with this. So I'm going to have here a carbon triple bonded to an oxygen. And I'll have 2 electrons here. Well, let's just count out. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the oxygen here is a complete octet. 1, 2, 3, 4, 5, 6, 7, 8. So is my carbon. That's 1, 2, 3, 4, 5, 6, 7, 8. So both of these have nice complete octets. So the formal charge on my carbon here is going to again be 4 valence electrons minus my lines, which is 3, plus 2 dots. So that's going to be a -1. And the formal charge on my oxygen, that's going to again be 6 valence electrons minus, there's my 3 lines and 2 dots. That's going to be a +1. And it still adds up to 0. So in reality, that's as good as we can get here. So my carbon here is going to be a negatively charged, and my oxygen is going to be a little bit positively charged. And that's just the way it is. Carbon dioxide is a little bit weird with this. Now, if you happen to start off on the other side and put your dots around the oxygen, you might say, well, maybe I could get a negative, or my formal charges to work out a little bit better in that case. But still, you have to watch your octet rule. So you basically want these things to have 8 electrons in it. If you violated that in some way, it just wouldn't work out for you. So again, that's going to be your structure there. All right, and then next up we can look at the cyanide. All right, and this is going to be very related to this. So cyanide, remember, is Cn-. So the valence electrons I have in this case are going to be 4 for the carbon, 5 for the nitrogen, but notice I have a -1 charge here. So I need to add this 1 extra one because of my -1 charge. So this is also going to have 10 valence electrons to it. So again, here's my carbon and my nitrogen. Do a little single bond thing here. And then again, I'm just going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And we can just calculate our formal charges for my carbon. Well, this is going to be exactly the same as what we just had up here. And for my nitrogen, that's basically the same thing, except now it's going to be 5 minus 1 plus 2. And now notice here, these things don't add up to 0. They add up to -1. But again, my total charge on my ion is -1. So yeah, that's perfectly fine. So we're just going to do the same thing, just trying to move these electrons around. So I'm just going to move these up here, move these over here. We're going to get a carbon triple bonded to a nitrogen. And then we're going to have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And we can very easily just calculate our formal charges on these again. So that's 3 lines, 2 dots. And now that's going to be, again, 3 lines, 2 dots. And here, that's -1, that's fine. So that means right here that my little charge on my carbon here is going to be the slightly -1. And again, that's just the way it works out. All right, another little example here is N2O, or dinitrogen monoxide, also known as nitrous oxide. So you know the laughing gas, that's the formula for that. All right, my number of valence electrons here, we have here for the nitrogen is going to be 5. We have 2 of them, plus 6 for the oxygen, so that's going to work out to be 16 valence electrons in this. Now here, what's going to be my central atom, because it's a little weird, we have the N2 in there. In this case, it turns out the nitrogen is going to be your central atom, and then you just put the nitrogen on the outside and the other oxygen on the outside, like this. So there's my central atom, nitrogen, and an oxygen, like this. Then we just put our bonds there. So it's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 11, 12, 13, 14, 15, 16. So what we also have to notice right here is that these nitrogens are not identical. So I'm just going to call this nitrogen 1 and nitrogen 2, just so we can keep track of them. So the formal charge on nitrogen 1, 5 valence electrons minus 1 line and 6 dots. It's going to be a -2. Formal charge on nitrogen 2, 5 valence electrons just like before, and I have 2 lines and no dots. And the formal charge on the oxygen, 6 valence electrons, and again 1 line and 6 dots. Of course, I add that up, -2 minus 1 plus 3, that's work out to be 0, so yep, that's calculated correctly. Now, of course, we notice here that this is a -2, that's a -1, this is a +3, so we want to get these closer to 0. Now, when we're dealing with this, we can move a couple of things around, but we have to be aware of this nitrogen already has 4 electrons around it. So that means we can only move a total of 2 pairs of electrons around here before we're going to get more than 8 electrons, which the nitrogen won't like. So what we're going to do here is basically, since this is like the most negative one here, I'm going to move this one over here and that one over there and try to get this thing here closer to 0 that way. So we're going to get here the nitrogen triple bonded to this nitrogen, single bonded to that oxygen. Now notice here this nitrogen has 1, 2, 3, 4, 5, 6, 7, 8, so that already has a complete octet. I can't put any more electrons on this nitrogen because, like I said earlier, these in this first row, they don't have any extra room for more than 8 electrons, so that nitrogen can't have any more than that. And then we're going to go here and put the rest. So that's already 8, and then 9, 10, because that's going to be now a complete octet, 11, 12, 13, 14, 15, 16. So again, let me just calculate my formal charges. And now there's 3 lines, 2 dots. And now there's just 4 lines and no dots. And I haven't changed anything, so that's going to be exactly the same as it was up here. And that's about as good as we can get for this. So this would be my structure here. This would be, a slightly positive over here. This would be slightly negative. Again, that's fine because if we have, the option, the oxygen is going to be more electronegative, right? Remember our little general trends. Fluorine is the most electronegative, then it kind of just works its way down. So oxygen is more electronegative than nitrogen. So the electrons like to stay over here on my oxygen like this. Okay, so that would be fine. Now there's actually another possibility that we could have tried. We could have had it like this, with a double bond between the nitrogen and the oxygen. So instead of moving 2 of these pairs over, I might have moved 1 of these pairs and then 1 of these pairs over here. And then we could go like so. So that'd be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And in this case, the formal charge on my first nitrogen, be 5 minus, and now I have 2 lines and 4 dots. This is still going to be exactly the same formal charge because that's going to, again, be 4 lines and no dots. And now this has 2 lines and 4 dots. Over here, we'll have a slight negative charge over here and a slight positive charge over here. But again, we basically have 2 possibilities. If you look at it, these are 2 possibilities, right? We have a negative one and a positive one, negative one and a positive one here. So these are 2 equally valid structures. But this one over here is going to be preferred because the oxygen is more electronegative. So this is why this one is actually preferred over this one. But in reality, these Lewis structures right here are going to be more in a resonance structure. Like I said, Lewis structures are good back of the envelope calculations, but they're not going to be totally 100% like reality actually is. So it's really going to be some kind of a resonance between these 2 structures. And actually, if we do the experimental studies on this, what we actually find is that it's really more like this, where this is going to be a 2.5 bond, and this is a 1.5 bond. So really, it's like I'm saying, basically you're taking the average between these 2 structures, and that's why I put here kind of like a little dotted line to represent a half of a bond. All right, Lewis structures can't really take in the whole idea of having half bonds or third bonds. It's just going to be a single, a double, a triple. In reality, you can get anything in between there. All right, now we can also look here at ozone. Okay, again, a deceptively simple one, but there's actually a lot of nice little subtleties with this. Okay, so ozone, of course, is just 3 oxygen atoms, so the valence electrons we have are just going to be 6 plus 6 plus 6, which is going to be 18 valence electrons. And this one is just, again, the things are going to be in line, no cyclic structures. So we're going to have here the oxygen with another oxygen, like that. And again, we'll just start putting our electrons on that side. So we have here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Now we just calculate our formal charges. And again, these oxygens aren't equivalent. So this is just going to be 1 and 2, and I'm going to put here a 3. All right. Now these 1 and 3 at this point are the same, but we'll see why we do this a little bit differently in a minute here. So the formal charge for the oxygen 1, so this is going to be 6 valence electrons minus 1 line and 6 dots. So that's going to be a -1. And oxygen 2 is going to be 6 minus, now I have here 1, 2, 3, 4, 2 lines and 2 dots. That's going to be a +2. And the formal charge on oxygen 3 is going to be exactly the same at this point as oxygen 1. Of course, I add all that up, and that's going to be 0. Now, at this point, you would say, all right, I will go here, move one of these over here, make a double bond. But here you have to be careful. This already has 1, 2, 3, 4, 5, 6. So I can only move one of these over. You might be very tempted to make double bonds on both sides, but at this point, you would violate the octet rule for oxygen, and that's a big no-no. Okay, so right here, that's why we have to stop. At this point, we can only do one little double bond. All right, and again, just doing my electrons, so it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So the formal charge on my oxygen 1, well, this is going to be exactly the same because I haven't touched it. Formal charge on my oxygen 2, and now I have here 3 lines and 2 dots. And we've seen this a bunch of times before, so that's 6 minus 4 lines and 2 dots, or 2 lines and 4 dots. Of course, that adds up to 0. Now, when I did this was completely arbitrary because I just happened to choose this one to go over here and make the double bond. Why couldn't I have chosen this oxygen 1 to make the double bond and left that one alone? Well, I just as easily could have. All right, so I could just as easily have done this. Right. So there's no reason I couldn't have done that, and in reality, this is what's going on. You basically have a resonance between those two possible structures. All right, so essentially, instead of having this either one of these structures being the reality, you just have the average between these two structures. So what we really have here is your oxygen, like so, with basically 1.5 bonds for each. Okay, so experimentally, each bond of these is equivalent, and it's going to basically be 1.5 bonds. All right, so that's what we actually do see. It's not a single bond, it's not a double bond, it's a 1.5 bond. All right, so this is what we're basically seeing. So these Lewis structures are saying, it's going between single and double bonds. In reality, you just take the average and you have a 1.5 bond for that. All right, so here's another little example, the NCS minus anion, which is actually called thiocyanate. So here, my number of valence electrons is going to be 5 for the nitrogen, plus 4 for the carbon, plus 6 here for the sulfur, because sulfur is right below oxygen. And then also, this is a -1 charge, so I'm going to need to add 1 more here for that electron. So that's just going to be equal to 16 valence electrons. So again, this one, actually, in this case, you might say, well, the first atom is going to be my central one. Actually, in this case, it's just written out in order. So we're just going to do N, C, and S. Now, I won't give you any kind of tricky ones like that, but just more to illustrate the point with these. So again, we just start adding single bonds in between there, and then we have your 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, and we just calculate our formal charges for my nitrogen. 5 valence electrons minus 1 line and 6 dots. That just has 2 lines and no dots. And 1 line and 6 dots. Add that up, and that's 0. So again, we want to go through here and move my electrons around. So we want to basically try to get these things closer to 0. So well, there's actually a couple of possibilities, because we can actually just move this one over, move that one over, move 2 of them over. So instead of me just drawing here, we'll just draw out the 3 possibilities and then just kind of calculate what my formal charges actually are. Okay, so these are my basic possibilities here. I have, and just notice I just went here to give 4 bonds to the carbon. So either I can have here 2 double bonds, a double and or a single and a triple, or a triple and a single. So that's basically what I can do for those. So this is going to be 1, 2, 3, 4, 5, 6, 7, 8, and I just have to put the rest around here. 9, 10, 11, 12, 13, 14, 15, 16. Down here again I have 8, 9, 10, 11, 12, 13, 14, 15, 16, or down here there's going to be 8 plus 9, 10, 11, 12, 13, 14, 15, 16. And then at this point I just have to go and calculate the formal charges for each of these. So here, for my nitrogens, each one of these is going to have, just like before, 5 valence electrons. All my carbons are going to have 4. All my sulfurs are going to have 6. So I can just put these in here really quick and just make our life a little bit faster. Okay, then for my nitrogen up here, that's going to be 2 lines and 4 dots. And then for my carbon, actually just notice right here, all my carbons just have 4 lines and no dots, so I can just solve those easily. Saving a little time here. And then for my sulfur, I have here 2 lines and 4 dots. Then down here, that has 1 line and 6 dots. And for my sulfur down here, that has 3 lines and 2 dots. And then for this one down here, I have 3 lines and 2 dots. And then for my sulfur, that has 1 line and 6 dots. And of course, if we just add these up, that's going to be a -1. It's going to be a -1. It's It's going to be a -1. We went through all these, and now which is going to be the most valid structure? Which one's going to have there? Well, this one right here, that one doesn't look really good because I have here a -2 and a +1. That just seems off. So this one's probably not going to be a nice valid structure. Then down here, I basically have a 0, 0, -1. Up here, I have a -1, 0, 0. So there's two possibilities. Which is going to be the more stable structure between the two of these? Well, in this case, if we just think about it, we want to look at our electronegativity. So this would say the nitrogen is going to have the negative charge, the sulfur is going to be 0. Down here, the nitrogen would be 0, and the sulfur would have the negative charge. So if we just think about our electronegativities again, actually the nitrogen winds up to be more electronegative than the sulfur. If you look at your little tables, nitrogen is more electronegative. So this means that the one with the negative charge and the nitrogen is going to be your more stable structure. So right here, the one with my nitrogen with the -1 on it, this is going to be my more stable structure like that. All right, there's another ion here called the cyanate, which is NCO-. So notice this one was NCS-. This is NCO-. So this is just replacing the sulfur by the oxygen, which is right above it. All right. So we could go through and recalculate all these, but really I can just substitute in the oxygen for all the sulfurs because the number of valence electrons is going to be exactly the same in both of these cases. So I can just go through here and figure out, well, which one's going to be the more stable structure. So I would have here NCO. Let's put my dots exactly the same places. The N double bond C double bond O. The N single bond C triple bond O. Or the N triple bond C single bond O. So these are, all exactly the same structures, except, the sulfur has been replaced by an oxygen. And since they have the same number of valence electrons, we're perfectly allowed to do that. Now you might be saying, okay, well, what is going to be my most stable structure? Well, you'd say, well, hey, this one was the stable structure over here for the sulfur. Why wouldn't this be the more stable one for the oxygen? But again, if we look here at a periodic table, oxygen is actually more electronegative than the nitrogen. So nitrogen was more electronegative than the sulfur, right? So now where basically these things have been moved around a little bit. So before, this was valid because my nitrogen over here had a slight little negative charge on it. But in this case, we're going to be wanting the oxygen to have the slight little negative charge. So that means that this structure down here is actually going to be my more valid one. So that one's going to have the negative charge on the oxygen, which we want because the nitrogen or the oxygen has a higher electronegativity value. Okay, do you want another example? Okay, you said no. Great, that's a great one. Nitrogen monoxide. All right, so nitrogen monoxide here has a valence electron of 5 for the nitrogen plus 6 for the oxygen, which is going to be 11. Now this one's tricky because we have 11. How are we going to get 8 electrons in here? Well, this is going to be one of those that, life is just not so simple. So for the nitrogen monoxide, there's going to be my N, there's going to be my O. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So notice right here, instead of having nice little pairs of electrons, I have a single electron all by its lonesome. So calculate our formal charges out. And there's going to be 1 line and 6 dots, which is going to be a -2. And the formal charge on my oxygen, 6 valence plus 1 line and 3 dots. So again, we'll just try moving these things around here. So what we can do is move one of those valence electrons around. We'll just move one of those up there. And we can't make this a triple bond because then we'd have this extra little oxygen around there, or this extra electron kind of floating around there. So we can basically just try this. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So this is going to formal charge on those. 2 lines and 4 dots. And that's 2 lines and 3 dots. Oops. Sorry, those should be negatives over here. The other possibility is, instead of having this single dot over here, what if I just move that extra electron over to this side, right? So I move that over to there. See if that works. So again, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So that's going to be 5 minus 1, 2 lines plus 3 dots. And again, that's 6 minus 2 plus 4. So this one right here would be my stable structure. So yeah, that nitrogen only has, 3 electrons on it, plus the other 2 that come from there. But, hey, that works. We can't have a complete octet because we simply just don't have enough electrons around. So, not all molecules are going to work out very nicely like that. So actually, this is what's called a free radical. All right, and this happens when you have an odd number of electrons because it's just simply impossible to pair all of them up. You can actually have free radicals also with paired electrons as well, but generally they're more and more common having the unpaired electrons like this. So if you have an electron like that, that's definitely going to be a free radical. All right, so here's another example, which is a free radical again. This is chlorine dioxide. All right, so my valence electrons, the chlorine here has 7, right, because he's one of the halogens. And then I have 2 oxygens, and that's it. So of course I add that up, that's going to be 12 plus 7, that's going to be 19 valence electrons on this. So again, I have another odd number. I'm definitely not going to have nice complete octets for these. So again, my first atom is going to be a central atom. Then I'm just going to stick 2 oxygens there, and then put on my single bonds and my rest of my electrons. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. Calculate my formal charges. And this has 2 lines and 3 dots. Oh, sorry. That has 6 over here. And then for my oxygen, that has 1 line and 6 dots. And of course, I have here 2 of them, so that still adds up to be 0. So when I do this, I want to move these to make them 0. Now you might be saying, well, wait a minute, my chlorine here, this already has 1, 2, 3, 4, 5, 6, 7. I really can't move any electrons around because that's going to violate the octet rule. But remember, that only really applies up to neon. Once you start getting to these atoms down here, we can start having expanded octets, so that's perfectly fine for those central atoms. So I can take, say, one of these, move him over there, take one of these, move him over there, and now this is going to work my chlorine to 0 and my oxygen to 0. So I'm going to have here the oxygen double bonded to the chlorine, double bonded to this oxygen. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. And we can just double check this. So there's 4 lines and 3 dots, which works out to be 0. And then for my oxygen, and again, there's our 4 lines and 2 dots we keep seeing. That happens to be 0. All right, so this is actually going to be our stable structure for this. And again, we just have that 1 extra little electron there. That's a free radical. This is also an expanded octet. Notice how many electrons this chlorine has. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There's actually 11 electrons on this central chlorine, but again, that's fine because the chlorine has the ability to borrow some neighboring electrons from it. All right, and then this is the last example I promised. There will be more examples for some more complicated molecules, but I'm going to hold those off until we go through the structures, because then we can start talking about the structures and solving all those for those particular molecules as well. So here we have nitrate. All right, so everyone should be knowing our nitrate anion now. So my valence electrons I have on this, we have here 5 for the nitrogen, plus 6, plus 6, plus 6 for the nitrogens, plus 1 more because I have a -1 charge. So that's going to be a total of 24 valence electrons. So my nitrogen is going to be my first part, and then I'm just going to stick my oxygens around, like so, and put single bonds between them. So that's going to be 1, 2, 3, 4, 5, 6 electrons. 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Right, there's my 24 electrons. Now we just want to look here, formal charge on my oxygen. So that's going to be 6 minus, and we've seen this a bunch of times already, 1 plus 6, so it's going to be -1. And the formal charge on my nitrogen, again, that's going to be 5 minus, now I just have 3 lines and no dots, so that's going to be a +2. And just remember this first one up here, I have 3 equivalent oxygens, so that's going to be multiplied by 3. So that's going to be -3 plus 2, you add those up, we get a -1, of course that's the charge on my anion, so we're happy. Now we can move again our electrons here to the nitrogen to help neutralize it out. But again, remember here, nitrogen already has 1, 2, 3, 4, 5, 6. The most I can actually move here is just 1. So I can just basically just choose 1, move that one over. So then I'm going to have here an oxygen double bonded to my nitrogen with 2 little single bonds coming out like so. And then I'm just going to fill this up. So there's 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. All right, so the formal charge on my double bonded oxygen that I have, that's going to be 6 minus 4 lines and 2 dots. Oh, whoops. Oh, 2 lines and 4 dots. Sorry, screw that up. 2 lines and 4 dots doesn't really make a difference. It's still going to be 0. the formal charge on my nitrogen is now going to be 5 minus, that has 4 lines and no dots. That's going to be a +1. And the formal charge on my singly bonded oxygens is going to be 6 minus the exact same thing, 1 line and 6 dots. And again, I of course have 2 of these left over. So again, my total charge on that's going to be -1. So this means that my nitrogen is going to have a slight positive charge. This is going to have a slight negative. That's going to be a slight negative charge. Now again, just like what we saw earlier here with the ozone, remember we had basically 2 possibilities and we could have these resonances and everything set up. Same thing is going to happen over here because, you know, I didn't have to choose this top one. I could have chosen, you know, the one to this side or this side. So in reality, there's actually going to be 3 possibilities for this. So I can have this one. So there's really 3 possibilities for these because, you know, they're all equivalent oxygens with these things. And again, experimentally, if you happen to look at this, what we really have there is going to be, you know, a nitrogen with basically 3 equivalent bonds, but, you know, they're just a little bit shorter. So all these bonds in here are really going to basically be about 1 1/3 bonds. All right, so they're not a single bond, they're not a double bond, but again, if you take the average among these 3 different structures, it works out to be about a 1 1/3 bond for each. So anyway, I shudder to think how long this one actually is, but I will stop this here, and then the next one will be coming up will be the shapes of the molecules and everything, and then will be another example one, basically, you know, going over this stuff a little bit more, and also looking at the shapes and the hybridization and everything. So anyway, stop this here.